Hello, this is Professor Snell talking to you about Environmental Systems 2. If you're wondering what I do on my Saturday mornings, this is it. I thought I'd go over exercise 6, the lighting calculations assignment. I wasn't sure if people were getting it in class, plus I promised, or I said that I would do a spreadsheet, and I didn't get to that, so I thought I would do that in a video. I may cut this into a couple videos. If not, then, or even if I do, obviously just scroll through if this review stuff is something you already know and you just want to get to the video, to the Excel portion. But I want to go through this assignment step by step and cover the basics. What are we doing here? We're saying, okay, we want to figure out how much light we need from our lighting fixtures so that we can specify them. So we can go find actual lighting fixtures that have the amount of light that we need and identify them. So the first thing we need to do is figure out how much light we need on our work surface in a given space. And so we're given this chart here. And we're going to use this method that assumes a fairly even distribution of light through the zones. So that's a very simplified approach. Of course, like everything else we do, this could get very complicated, and we have people who are specifically involved in lighting design who know, who are going to be the go-to for the more complicated equations. Like I'm always saying, as architects, we're just trying to get, a lot of times we're just trying to rough things in so that it's reasonable, and then other people are going to adjust it. In this class, we're just trying to understand the concepts. So for example, this chart, I don't know if this is up to date because light level requirements change, and there was actually a slide in the slides we presented saying that there was a huge change in the last 50 years in the United States in terms of task lighting that's required. The amount of light level is much less now than we used to say. Anyway, I don't care because I'm just talking about concepts. This was an assignment we inherited, so I don't know where this chart came from. The point here, though, is that we have a room type and then light levels. The room type is defining the task or the activity, and here we can just, if we just look at these basic criteria, in a cafeteria, we're saying that our light level would be 20 to 30 foot candles. In a classroom, it would be a little bit more, 30 to 50. In a corridor, it would be much less. That makes sense, right? In a corridor, we don't really need to see that well. We're not doing tasks in the we need to make sure that we can get through the corridor and we're comfortable there. But we don't need we're not doing detailed tasks, so we don't need as much light. In a gymnasium, this is a workout gymnasium, 20 to 30, more in a sports gymnasium, 30 to 50. You start getting into classrooms, it's more. Professional laboratory, even more. Let's see if we have like offices. Offices 30 to 50. So in the middle, workshop more. So the point is that this makes sense, right? There's more light for things where we need more detailed tasks. But really, what is a light level, and why are some in foot candle? Why do we have foot candles and lux? We've talked about that, but maybe it's confusing. So let's go over that. And let's just say we're going to skip power density. We've mentioned it briefly, watts per square foot. It's important, but not for this assignment, this concept right now, so we're not going to worry about it. This is about how much power we're getting from the light, or how much light per unit of power. So this is about the efficiency of the light. So what is this whole foot candles lux thing? So if we have a candle or a light source, it's going to illuminate a sphere around it, right? And that sphere is going to have a radius. And so the area of the sphere is going to be 4 pi r squared. So the 4 pi is a constant. So it's the r square, the radius, that determines the area of this sphere. And as it increases, the area increases by the square of the radius. That's important. So in terms of our little light here, though, we're talking about luminous flux. Sorry about my handwriting. I'm still trying to figure out how to use this pen. I just ordered a screensaver that is supposedly going to make this feel more like a piece of paper, so maybe it'll be better when I get that, but we'll see. So luminous flux is in lumens. That kind of makes sense. It's also called candle power. That's the IP unit, inch pound. CP, or candela is the SI unit. I think they're equivalent. I don't ever really use them, so, but CD if you see that. And that's the amount of light going in all directions out from that lamp. Now that's lumens. That's good. That's how we determine the amount of light that a lamp is producing. And a lamp is a bulb, so there can be multiple lamps in a fixture. But what we're more interested in now, because what we're talking about is if we have a light up here that's putting out light, you know, here's our ceiling. We want to know how much light is hitting a surface down below. All right? So we want to know how much light is hitting this surface. So we need to know how much light is hitting a specific area on our sphere. I guess I'm just zoomed out. Oh, that's what it is. I'm zoomed way out. Okay. So that means then, so this is our square, this is that same square foot. This is our light up here. This is that. So now if we think of it like we've seen it drawn, like we have this light and we're going out 1 foot. You know what I'm going to do? I'm going to come down here and zoom in. Yeah, because I was zoomed out, so I didn't have a lot of fidelity in my my pen. So if I now have my little candle here, and I'm going 1 foot away, and so now I've got that 1 foot, 1 foot by 1 foot. And this is that square foot that we were talking about, you know, on the surface of the sphere. This is luminous intensity. Still in lumens, because even if we, you know, it's the same. This light is putting out lumens. It's also putting out lumens in a direction, right, toward this square foot. So it's in lumens. But when we get here, this is now illumination. And it's lumens per square foot, or foot candles. Kind of makes sense because we're a foot away from the candle, so it's a foot candle. Now, if we go further, and we're now out at a meter away, so 1 meter, and this is 1 meter by 1 meter. This is now lumens per square meter, duh. And that's a lux. And 1 foot candle equals about 10.75 lux. And that's simply because of this relationship. Right? So as we get further away, so like the difference between 1 foot and 1 meter from this light source, these should be on the same axis, obviously. Then we get much less light hitting this surface because it's further away, and that's the amount of light hitting it is being reduced by the square. By the way, and this is why here we're saying that we have, it's about 10 times more. It's actually, if you look at it, if you look it up, it's 10.75 lux per foot candle. But, you know, often we'll just round. That sure is convenient just to say times 10, so that may work for us in terms of what we're trying to do. Okay. So this is where then the foot candles and the lux are coming from. And the main thing to remember is that it is lumens per area, per unit area. So if we come back to our assignment document, we now know, okay, at least I get light level is illumination. It's how much light is hitting our task surface, which could be a floor, it could be a table. So it's the height of it's determined by the space itself. We can look that up in this chart. So now we know how much light we want illuminating our task surface. The next step, okay, I got called away, so it may not make complete sense, this transition here. Let me make sure that the speakers still seem like they're on. Okay, so we now know how to figure out the illumination, the illuminance that we need on our surface. But now we're given this equation here that illuminance, so we know that illuminance is lumens per square foot per area, right? Then why do we have the rest of this stuff here, this coefficient of utilization and light loss factor? Well, it's because this is the real world, and a light fixture is not going to, that's rated at a certain number of lumens, is not going to actually put that number of lumens onto the area we're talking about because of some real world factors. This is a simplification right now, so it's an estimate. And the way we're doing this is just one way. But the point is we're trying to get from fantasy, from vision to reality with some other variables. So what are they? Before we get to that, let's just go through everything they're saying here. Is that they're just mentioning to us, remember that when we do get the total lumens, that's going to be the number of lamps times the lumens per lamp. So if we have 100 or 1,000 lumens, and this is way low, and then we knew that we had 2 fluorescent fixtures in a space that we wanted to have over it, then each of these is going to have 500 lumens. If it was a fixture that had 3 lamps in it, then each of these would have to have a third of that 500 lumens, right? So it's just saying, fairly straightforward, but just reminding us that we're going to find a total number of lumens that we need, and then we're going to need to figure out how many lamps we have so we can figure out the actual lamps that we're going to need to specify. And then they're also pointing out that a lamp is a bulb, not a fixture. I think I've said that a couple times already. Okay, so then what is this coefficient of utilization? It's determined first by the cavity ratio, and they give us this equation: 5 times height of the fixture to work surface times room length plus room width divided by room length times room width. Okay, what does that mean? So let's go figure that out. If I have a room, a space that I'm illuminating, it's going to have a width and a length and a height. And what we're saying here is that this geometry is going to have some effect on how much light from a fixture actually gets to a work surface. So, for example, if our fixture is below the ceiling, this is our fixture here, this is our lights, and we're lighting a table, a desk, then our height is going to be from the top of the lamp, or the bottom of the lamp, or the bottom of the light fixture to the top of the work surface. So if we're talking about a gym, that would probably be all the way to the floor. If we're talking about an office, it's going to be to the desk. So this is going to be different for different spaces. Might not be to the ceiling. Actually, let's do it this way. So that's the first point. But now we've got, so what is this cavity ratio equation? It's cavity ratio equals 5, which is just a constant. We're not going to worry about that. The reason we're doing this is that we want to understand equations so that we aren't just blindly applying them. It helps us troubleshoot, and you'll see why here in a second. And also, it's just, we don't want to be afraid of equations. They're often very straightforward if you kind of dig into them and maybe you don't understand the math completely, but you go, oh, I get the relationship here. That's what we're talking about. So this 5 is some kind of constant. Let's just say it has something to do with an assumption about the surfaces of the room. But I don't really know. 5 times the height, so we've already said that that's going to be to the work surface, times the width plus the length, all divided by the width times the length, so the area. And so what we're really saying is this, because this is a constant, this is going to be set by the geometry. So if the width and length changes, this height would change based on the design. And would be the same based on the design. This height here wouldn't necessarily change if we're changing the width and length of the building. So this is really about width plus length over width times length. And that's perimeter over area. Now, it's not, the perimeter would be this times 2, right? But we're talking about a relationship here, so we don't need the times 2. We're saying what's the relationship between the perimeter of the space and its area? So let's dive into that for a second. Let's say we had a space that's 5 by 5 units. So we're looking in plan now. And then we had another space that's 1 by 25. These have the same area. Area equals 25, right? But the perimeter of this one is 5 plus 5, or the perimeter in terms of our equation is 5 plus 5 divided by 25. So that's 10. Let's do it this way. 10 divided by 25, which equals 0.4. This is 25 plus 1 for our perimeter, divided by 25. And 26 divided by 25 is about 1. So the point is that as we get longer and thinner, the relationship between, as the space gets longer and thinner, our cavity ratio is going to go up. Because if this is 1, it's going to be more, and if it's 0.4, it's going to be less. And if the height goes up, the cavity ratio is going to go up. So it seems like a larger cavity ratio means less light on the surface. Let's see if that works, because that's intuitively, I would think, well, that's weird, because it seems like we're talking about reducing the amount of light. Because to me, the idea is here, if I've got a light here, it's going to be less efficient at getting out to here and here than a light right here is going to be. So this should be more light, not less. So if we look at our equation, though, cavity ratio once we have the cavity ratio, then we look it up in this table, and as it goes up, then the actual coefficient of utilization goes down. So as this is going up, these are going down. So it's an inverse relationship how they've calculated this. And you could do it the opposite way, right? Because we're just creating a relationship. So if we had, for example, let's go look at the sample they gave us. Just to show. So what they're saying here is we have a space that's 20 by 40 by 9 feet. So we use our cavity ratio equation to get 3.6. Then they went and looked at this coefficient of utilization chart. You use your cavity ratio, which in our case is 3.6, which would be right here. The people who made this just rounded down to 5.1. And all that's going on here is that you say that they have three basic task criteria. First is for spaces with tasks subjected to veiling reflections and where visual comfort is important. So you can go look up veiling reflections. As simple as, if I'm looking at a book in a library, the way the light is hitting it is going to affect, so the angle from which it comes in is going to affect the way I see it and the amount of glare I see. That and there's other factors that create comfort based on where the light is situated. So that's what we're talking about here. And so if we're saying that the space has veiling reflections and visual comfort is important, then our cavity ratio is going to be smaller for the same, our coefficient of utilization is going to be smaller for the same cavity ratio. If we have a space without tasks where visual comfort is not a criterion, it's larger. So this is just a way of creating a coefficient of utilization based on what we're doing in the space. And the thing to take away here is that coefficient of utilization is simply a variable that we calculate very roughly that takes into consideration the geometry of the space and how accurate or how much light we need based on the task, and this also where the light is situated. So that's where the veiling reflection stuff comes in. You don't need to understand that directly. You just need to pick one of these three options, and there is no right or wrong, and then pick a value. So like if I thought it was my space without tasks, or with tasks not subject to veiling reflections, but where visual comfort was important, I was thinking that might be a gem. I would probably make this like 0.48 or something, because I'm at 0.36. But whatever you chose, as long as it was reasonable, I would not say there was a right or wrong answer. And it's called coefficient of utilization because we're saying how much of the light can we utilize in the physical geometry of the space. Okay? So the point here is, and the reason I'm going through this is because that, if we didn't cover that, or if you get too bogged down in it, that could be really confusing. But all we're saying is that we're trying to make our lumens to area make more sense. So we're bringing in two different variables. One of them is coefficient of utilization that has to do with geometry of the space. And the higher, and it's related to the cavity ratio. Because of this chart, the higher the cavity ratio, the lower the coefficient of utilization. Okay. Now, what's the next one? We have this light loss factor. What is that? Well, it's pretty descriptive. It's saying we've got a light that is rated at a specific number of lumens, so an output, a luminous flux output. Luminous flux, we go, what was that again? And, oops, we come back to here. We remember that luminous flux, and see now I'm getting that lag. Luminous flux was the amount of light coming out of the intensity of the light coming out off the light surface in all directions, and then luminous intensity was the amount going in a specific direction that led to illumination. Now, light loss factor is simply, and there's a variety of ways this is calculated. We're doing it a very simple one. You could look up different stuff, there's different variables that can be taken into consideration for this. I'm getting that lag again. It drives me crazy because it works sometimes and sometimes it doesn't. I don't get it. I'm talking to IT about it. Anyway, so light loss factor is, first of all, is there dirt on the light? You just assume, well, there's going to be some dirt. So we're gonna reduce the amount of light coming out of the lamp compared to what it's rated for. Also, some types of lamps become less efficient, or they degrade more quickly. So a certain kind of lamp, we might say, okay, we're going to have a little bit, we're going to say it has less, we're going to assume that after a year it's at 80%, whereas this other light we're going to assume is at 90%. So where the light is situated exactly in terms of like, is most of the light going up as opposed to down? So you would have, if you have 1,000 lumens, but most of it's going to hit the ceiling, then that's less of that's going to hit the task. So that's all the light loss factors take into consideration. So how does it work? We start with this assumption that every light we're going to say is just 92% efficient. So we start with 0.92 times the number of lumens for any light. That's the first part of light loss factor in this calculation we're doing. Then, in a very simple step, we say, okay, we've got a bunch of different categories, 6 different categories to find in this chart, and they describe different types of situations that the light are in, both in the room and also how they are directing the light. So like a semi-direct free lamp, bare lamp, strip lamps would have a 0.88. So if you think your lamps are that, then you're going to choose 0.88. If there's less than 15% going up, or it's open louvered, then you're going to pick 0.85, etc. Now, again, there's no right or wrong. You're learning by doing this, so don't go, I don't know how to do this. Just look at these descriptions and say, yeah, this light that I've chosen or that I'm going to choose, or in my room, like if I'm doing, I'm in my gym and I've got some kind of light like this, there's like a cage with a bulb in it. What do I think how does that translate to one of these 6 categories? No right or wrong. You just need to pick one. The point to notice is that they're multiplied together. So if we go down to the example and we go to light loss factor, what they've done here is they're saying, okay, that's the default. Every lamp's going to be at 0.92 to begin with. And then because they said we want to just do completely indirect light, we're going to say it's 0.88. That's category 1. And then we multiply these 2 together and we get 0.81. And that is then, if we go back to our equation, the light loss factor is being multiplied by the COU and the lumens. So it's always going to be a fraction. So if we're at 0.81, that means only 80% of the lumens are going to be available due to dust and the way the light is situated and other factors. So the light loss factor takes the number of lumens down. The coefficient of utilization takes the number of lumens down. And we know that because, remember, these are all going down here. So the point is, it makes sense. We have our original lumens per unit area, and then we've got 2 adjustment factors that are taking that down so that we will get an adjusted amount of illuminance based on the real world. All right, so now we can look at their example and take the next step. Oops. So in their example, they make the point that, or in our example, we're given a luminance. That's what we're looking up in the chart. And that's this equation that we've just been dealing with. But what we need is lumens, so we need to rearrange this. So we need to say lumens equals, okay, a luminance is in the numerator. Area then, comes up to the numerator area, and the rest of the stuff is in the denominator, coefficient of utilization times light loss factor. So this is our actual equation. And if we look at so here's their example. They're saying if we're in a room that has a geometry of 9 feet for a height, 20 by 40 for a width. Well, we're actually up here. And we've already looked up that our space needs 75 foot candles in illumination. We calculate our cavity ratio with our equation for cavity ratio, come up with 3.6. We choose the second task criteria. A task is either without task, the space, or does not have veiling reflections, but where visual comfort is important. I think that would be a gym. They're saying 0.51 because they rounded down. I would think you would actually go the other way. So I would make this a little different, but I'm not going to worry about it. They picked a light loss factor of 0.88 based on complete indirect lighting, which would be category 1. Then they just plug these numbers into the equation. 75 foot candles times the area divided by the coefficient of utilization and the light loss factor, we get 145,000 lumens. Then they're saying in their design they have 60 lamps. That's not 60 fixtures, that's 60 lamps. And so that means that each lamp would need to put out 2,400 lumens. So if I found a fixture that had 4 lamps in it, then each of those lamps would need to put out 600 lumens, right? And then there's some descriptions that you should read about, how you would use this. And I'll talk about that probably when I get to the next portion of this, the actual spreadsheet. And then the deliverables are defined down here. But all I want to do in this first video, I realize now I'm going to do is just separate these out, is get us to where we can make this calculation and understand what it's about. I think I've accomplished that. If you have any questions, ask me about it, of course. Now, for part 2 of this video, I'm going to create a calculator that allows us to make this equation simply, because we're going to have to do this for each room. And you'll see the deliverables require that I want to see the cavity ratio, the coefficient of utilization, the light loss factor, etc. for each room. So if you have a calculator that outputs those things, then you can do it over and over again really quickly and don't have to, and you can check yourself, because if you have constants in Excel, you can be confident in your equations, whereas you can make a mistake in an individual equation if you're doing it by hand. All right, so let's move on to that.